So welcome to class 24 of chemistry at My Fun Science with Mr. Leingang. I hope you all had a good week. Last week you were finishing up module number 11. And since it was the fourth module of the second semester, it meant that you were also taking a test over modules 8, 9, 10, and 11. Although nobody opted to take the test, you're all waiting until after today, after our lesson today, to take the test. So hopefully you came here with good questions to ask, and hopefully I'm able to provide good answers to help connect the dots for you so that you're all ready to go. Of course, as you are into a new week, you've also got new assignments this week. So in addition to your test, you've got the stuff that you're going to be doing for module number 20 or module number 12. So here we'll be getting started on a new module, new material. We're going to be going in and taking a look at solutions and the different things around that. Before we get into any of the science, we want to start with a word of prayer. So if there are things going on in your life, in your family, in your community that you'd like some prayer support for, you can share that in our meeting chat, and I'd be delighted to be able to pray for you. Otherwise, we will take a moment to say hi to those of you who are logged into the live class, and then we will pray and get into our materials. So let me do that. Welcome, Addison. Good morning, Caroline. Good to see you, Jared. Nice to have you here, Lance. Welcome, Meadow Lynn. Nice to see you, Sam, and welcome, Whitley. Oh, Addison, that's so tragic. I'm sorry to hear that. Of course. Maybe there are other prayer requests. If you are typing one in, finish that up, and we will then get it on into our class prayer. But let's go ahead and get started. Would you join me? Lord Jesus, we thank you for hearing our prayer and knowing that you are with us, that you are for us, that you proved that by dying in our place and offering to us your righteousness. And so we come to you in that with hearts that are filled with gratitude for your gifts of grace. And we pray that you would help us to remember that, to remember who we are in you and what you have done for us. I pray for these students as they're in class today. Help them to be attentive so that they can hear well, that they can remember well what we talk about. And Lord, especially if there are any worries and concerns about the concepts covered on the upcoming test, that Lord, you would quiet those so that they are not a distraction to the student, but rather you would use them to move and motivate the student to do the studying necessary. And then, Lord, I pray that as they go to take the test, you would just help them to be focused, to be able to remember and to do well, and that it would be an accurate reflection of what they have been studying and learning. Now, Lord, thank you that as we study creation, it's more than just an academic exercise, because you reveal yourself in part through the world around us. And so pray that you'd open our eyes to see that as well. We want to lift up and pray for this family that Addison knows through her teammate who's just tragic loss here. We pray that, Lord, you draw near to them, strengthen and comfort them. And as family and friends are just reeling with the shock of this sudden loss, Lord, I pray that that hurt and that hardship would drive them to you, and they would discover that you can and will comfort them. Thank you that you can identify with what it's like to lose a child. And we want to pray too for Meadowland's dad, who's off working this week. Help him to have a good week, a productive week, keep him safe, help him to have a good time. And when it's all said and done, Lord, bring him home again. We pray with Sam for this family friend. Pray that, Lord, whatever's going on medically that's caused all this time in the hospital and this recent surgery, that Lord, that surgery would repair it, would fix it, would correct it. Lord, that you would touch and heal his body, and that he wouldn't have to continue to be dealing with this issue or impacted by it. And just pray that you'd bring this to resolution. And thank you that Sam and his family care enough about this friend that they are lifting him up to you in prayer. If there are other ways that they can bless and serve this individual, I pray that you'd help them to see it and to act on it. And Lord, for all that we do, we just commit it to you and seek to do it in a way that would reflect your presence with us. And we know that you love us. We also know that we love others because you first loved us. So help us to do that in a way that brings glory and honor to you. And we pray these things in Jesus' name. Amen. Okay, so class number 24. We just finished solutions. We're going to be doing gases. I got confused. I was talking earlier about what we're doing and where we're going. And I have another chemistry class later today with another school, a private school in California that I teach for. And the curriculum that school uses does it in exact opposite order. So they just did gases. And then now that today they're going to go into solutions. You just did solutions, and then we're going to go into gases. So I apologize. I misspoke earlier. I hope that didn't alarm anybody too terribly. So we did this unit on solutions. We did a lot of vocabulary talking about things that were soluble or insoluble, things that could become saturated or super saturated, things that would dissolve, or things that would precipitate. And we talked about how to calculate the concentration of that. That concentration could be in molarity, which was moles per liter. It could also be in molality, which is moles per kilogram. We like molality because it allows us to calculate how the freezing point or the boiling point changes when a solute is added to a solvent, creating a solution. And so we take our equation, depending on whether we're working on freezing point or boiling point. We've got that standard, and then multiplying that through in order to be able to calculate what the difference is. Of course, remembering that then that needs to be added or subtracted to the original temperature in order to be able to tell you what the new temperature, the new boiling point or freezing point would be. So, okay, quick summary. You guys had seen that slide last week as well. So let's get right on into homework questions. When I was going through the homework over the weekend and entering grades into the grade book, it looked like there were a number of students that had struggled with some of these questions. So which ones would you like us to take a look at as we review module 11? Which ones should we take a look at today? I don't see any quick responses. Oh, there we go. There's a little bit. Addison says 11.3. I think we certainly can, especially with everybody else being silent. Like I said, don't feel bad if you struggled. Lots of students struggle. Of course, with the test today, we want to make sure that you figure out what you did wrong, whatever that might be, so that you know it before you have to go take the test. So if you haven't already, take a quick look. I am doing the same myself here, taking a quick look, making some quick adjustments to the grade book. All right, so we'll take a look at that one. Sam says 11.5. We can certainly look at that one. All right, so give me a sec here and we will pull those up. I'm going to pull them up on my other screen here so that we can, I can just copy and paste onto my whiteboard. Okay. So we're doing, let's see, practice problem 11.3. And okay, practice problem 11.3. Here is our reaction. And it says, if you've got 345 milliliters of a 1.25 aluminum nitrate solution added to an excess of sodium sulfate, how many grams of aluminum sulfate will be produced? Is this the right question? First of all, let's just kind of make sure I'm on the right spot. Phantasmic. Okay. So I have, let's see, volume. I've got a molarity. I'm asked for grams. So here's the trick. I know from stoichiometry that I can go moles of A to moles of B using the molar ratio, right? And I know that I can go grams of A into moles of A using the molar mass. But I'm not given grams and I'm not given moles of the aluminum nitrate. So how do I go from milliliters to grams? Milliliters of one thing to grams of something else. Well, I've got to figure out how to get into moles of aluminum nitrate. How am I going to get to moles of aluminum nitrate? Well, you'll notice that they give you this volume and the molarity. So we need to remember that molarity is equal to the moles of the substance divided by the volume. So there, when I see it that way, if I want to know moles, I've got to ask myself, do I know the molarity and do I know the volume? If I know two of the three, then I can solve for the one unknown. And it turns out I do. I do know the molarity. The molarity is 1.25. And the volume is 345 milliliters. Now, since molarity is moles per liter, I cannot leave my volume in milliliters. I've got to convert that to liters. So 345 liters by now you probably know is 0.345 liters. I could show you the conversion for that. If you've got 345 milliliters, you know there's 1,000 milliliter in every 1 liter. And so you're multiplying 345 by 1, divide by 1,000. That moves the decimal 3. And your answer ends up being 0.345 liters. So that's how I did that. Now solve for the unknown. I need to get to where I have moles. So 0.345 is divided into moles. I'm going to do the opposite operation to move it to the opposite side of the equation. And therefore, it becomes the moles of aluminum nitrate, AlNO3 is equal to 1.25 times 0.345. And I could check my units if I wanted to in order to see if that works out to be right. The 1.25 was this capital M, which stands for molality. Molality is really moles per liter. And then the 0.345 is liters. What happens if I take moles per liters and I multiply it by liters? Well, the liters are going to cancel out. Pardon my typo. And you're going to be left with moles. Moles is exactly what I wanted. Okay, so my units check out. Now I just need to get my calculator out and figure out what does this mean for moles. My handy dandy calculator built into my computer here. 1.25 times 0.345. Calculator says it's 0.3125. Of course, I'm going to limit myself to 3 significant figures. So to keep the 3 highest place values, look at the next one. Do I round up or round down? In this case, round down. And it becomes 0.431 moles, not miles. Sorry. Yep. Addison, a little typo there. Be careful. That 0.431 becomes 0.421, right? Oops. Yep. Right. Okay. So 0.431 moles. All right. Now I'm in moles. So now this just becomes an old-fashioned stoichiometry. I have moles of one thing. I want to convert into moles of the other. And then I have to go from the moles of that thing into grams of that thing. Because ultimately, that's what I'm asked to solve for, is grams. So I'm going to get rid of my calculator here. We're going to start with what we know, 0.431 moles of A, that is AlNO3. If I type that in all the time, it's going to take up way too much space. So I'm just going to use an A to represent that molecule. All right, now, when you want to convert from moles of A to moles of B, use your molar ratio. What is the molar ratio? Well, we know according to the balanced equation that it is 2 moles of A for every 1 mole of Al2SO43. Again, if I take that all out, I'm going to run out of space, so I'm going to call it B. 2 to 1 molar ratio. 2, that's the coefficient, 2, 1. Now I could calculate out what that is, but I could also just do this last part as a single step. Once I'm in moles of B, if I want to go from moles to grams, I'm going to use the molar mass. So, well, okay, I have to calculate the molar mass. What is the molar mass? Well, I get up my periodic table and I look up aluminum. And aluminum in my periodic table is 26.98. There are 2 of them. So I need to remember this is going to be times 2. Then I look up my sulfur. My sulfur is 32.07. There are 3 of them. Why? Because there's a 3 outside the parentheses and a 1 inside. 3 times 1, 3 sulfur. Oxygen is 16.00, and there are 12 of them. How is that? Well, because there's a 3 outside the parentheses, a 4 inside the parentheses. 3 times 4 is 12. And so it's kind of a complicated little, math problem. Not terrible, but I got to do it. 26.98 times 2. I'm going to add that, and then I'm going to start using parentheses to the quantity of 32.07 times 3, end parentheses. And then I'm going to add that to the 16.00 times 12, end parentheses. And now I'm going to hit my equal sign. And it says the molar mass of aluminum sulfate is 342.17 grams per mole. So I'm going to put that as my next part of the conversion. Moles on top, so there's got to be moles on the bottom. 1 mole of aluminum sulfate has 342.17 grams. Moles of A cancels moles of A, moles of B cancels moles of B. I'm left with grams of aluminum sulfate, which is what I want. Get my calculator out once more, and I get my answer. 0.431 divide by 2 times 342.17. My calculator tells me the answer should be 73.737635. Now I got to stop and think about significant figures. I had 3 significant figures in my calculation for the mole, so I'm going to be 3 significant figures here. Keep the 3 highest place values. Look at the 4th one, which is the 3 after the 7 to the right of the decimal. Ask, does that round up or round down? In this case, it rounds down, so it just basically drops away. And I have 73.7 grams. How'd that compare? Did I do it right? Well, Sam, you probably used different numbers. You used 27 instead of 26.98. I was looking at a different periodic table. If I look in my textbook, I look up aluminum and it's 27, not 26. My sulfur would be 32.1. And so ultimately, that's where the difference is. It's a difference of significant figures. I mean, we could do that. The concept doesn't change. This becomes 27. This is 26.1. I think this is still 16. All right, so get my calculator out. 27 times 2 plus the quantity of 32.1 times 3, end parentheses, plus the quantity of 16 times 12, end parentheses, equal, and I get 342.3. 342.3. Now, if I do this, 342.3, so we come back here, 0.431 divided by 2 times 342.3. My answer is 23.76 or 73.76. And so I end up with 73.8. Oh, I still don't have exactly what you have. Why not? What did I do wrong? Did I do something else wrong? I don't see what else I did wrong, but I don't know. I must be making something somewhere. The process is the same. 3 sig figs, 3 sig figs. Did I not do 26 in my 27 in my calculation? Let's look at my history. Let's see. No, I got 27 times 2. 27 times 2. Was 54, and then that 54, 32.1, 16. Is it, let's see, 27, 32.31, oh, 32.1, yep. 32.222 to 32.1, yep. And 16.0. 342.15. Either way, here the point here isn't a tenth of a gram, but do you know the process? The trick here is knowing that when you're given the volume and the molarity, that from that you can calculate moles. And once you know moles, the rest of the problem should fall into place. Okay, so there was another one that was asked. Let me go back up. I got to scroll back and see. It was 11.5. Okay, so this was 3. Let's clear the board. We'll move on to 11.5. $11.5. All right, very wordy problem. 11.5, one popular test for lead, which is Pb2 plus ion, contamination in drinking water is the chloride test. This test involves adding sodium chloride to water. Any lead 2 plus ions in the water will immediately react with the negative chloride, forming a solid precipitate. And then they give us the equation. Okay. So here's our equation. Measuring the mass of this precipitate can tell you what the concentration of lead 2 is in the water. If an excess of sodium chloride is added to 1.6 liters of water and 25 grams of PbCl2 are produced, what was the molarity of Pb2 plus in the water? Okay, so there's our problem. Okay, what's our problem? Well, we've got our balanced equation up atop. Okay, that's good. Get that to where we can see it. We've got a volume of water and mass of PbCl2. And we're asked the molarity of the Pb2 plus in the water. So one thing that can sometimes be helpful is to write out, what do you know? What do you need? in this case, what do I know? I know the volume and the volume of the solvent. I know the mass of the solute, right? So in other words, I know really the molarity of the PbCl2. But what we're really asked for is the molarity of the Pb2 plus. We're told that the mass of the Pb2 plus is going to be related to the mass of the NaCl, right? They told us the Pb2 plus is going to form, going to react to the Cl, and so we can measure the mass of the precipitate to tell us the concentration of the Pb2 plus. The relationship between the Pb2 plus and the Na plus is a 1:2 molar ratio, or the NaCl is a 1:2 molar ratio. So we're going to need to account for that in our calculation. Okay. This is 5. There we go. Stoichiometry problem always starts with what you know. What do I know? 25 grams of PbCl2. Well, okay, where can I go from there? I know that. I want to go from grams to moles, because whenever I'm comparing two things, I can only do that comparison by moles, not by mass. So I got to ask, how many moles of PbCl2 do I have? In order to get that, you got to multiply it by the mass, by the molar mass. So we're going to ask, how many grams are in 1 mole of PbCl2? And look it up in my periodic table. My lead, here, I'll use your book's periodic table this time. Hopefully that will reduce the chances of my being off a little bit. Let's see. Lead is 207.2. And chlorine is 35.5. And there's 2 chlorines. So 207.2 plus 35.5 plus 35.5. And my calculator tells me it's 278.2 grams per mole. Anybody confirm that? Did I do that all right? Now, ultimately, when I go to use that number, I don't want to be more precise, but what I'm doing is addition. So your precision is to the place value. All 3 numbers I added are precise to the 10th place. So I will leave my number to the 10th place, and that makes 278.2 grams. Okay, so how many moles? Now we got to do our 25.0 divide by 278.2, and the moles of PbCl was 0.0 8, 9, 8, 6, 3, 4, on and on it goes. 25.0 grams has only 3 significant figures. So I'm going to be limited to 3 significant figures here. Keep the highest 3 place values. Look at the next one. I asked, do I round up or round down? 0.08986 rounds up to 0.0899 moles of PbCl2. Are you with me so far? All right. So now we're in moles of PbCl2. Where do we go from there? Well, now that we've got the moles of the PbCl2, we can actually make the comparison to the moles of Pb, because that's ultimately what we're asked for, right? What's the molarity of the Pb2 plus? So we're going from here to here, which according to our equation is a 1-to-1 molar ratio. So that's pretty easy math. I can just simply say it's going to be 0.0899 moles. Come on, fingers, get on the right keys, of Pb 2 plus. Okay, well, I wasn't asked the moles of Pb2 plus. I was asked the molarity of Pb2 plus. So I got to figure out, what does that mean practically speaking? Well, we know that molarity of anything is equal to the moles of the solute to the liters of the solvent or the solution, right? So it's going to be moles per liters. Okay, well, how many moles do I have? Well, we just calculated that. We know the moles is 0.0899. What is the liters of solution then? Well, they gave it to us in the problem, 1.6 liters. So the volume has not changed. Get your calculator out, 0.0899 divide by 1.6, and you end up with 0.0562656146. Looking at my numbers, am I going to round up or round down? Well, 1.6 is 2 significant figures, so my answer is going to be 2 sig figs. I'll keep the 2 highest place values. I look at the next one, which is 1, asked, do I round up or round down? In this case, it rounds down. So 0.056 molarity. Yeah, it's one of the reasons why I recommend to students whenever we do word problems. I don't know, have you been through the challenging word problem section of your math experience? Like, I remember for me, it was like 7th or 8th grade. I think it was 7th grade when they introduced in algebra the idea of word problems. And you had all this information. You had to figure out what am I really supposed to do? And it could be really, really hard. And one of the ways that we can overcome that is by disciplining ourselves to really focusing on the parts. What do I know? What do I need? And what factors in chemistry What factors will get me from what I know to what I need? And if you're going to write out, what do I know? You'd say, well, I know the volume, 1.6 liters, right? And I know the mass of PbCl2 is 25 grams. And you say, well, what do I need? Okay, well, what do I need? What I need is the molarity, which is moles per liter of Pb2 plus. Now, you might be tempted to say to yourself, well, okay, I have this liters here, I have mass here. Can't I just from this mass determine moles and then have molarity? But you got to remember, this is Pb, not Pb2 plus. So if you had done that, you would have actually gotten the right answer. But theoretically, you also had to account for the mole change. So even if you just listed this out and you sort of did it wrong, you said, well, okay, I need moles per liter. I have mass. I can find moles. I know how to go from mass to moles. And then moles per liter gives me the answer. In this case, that would have given you the answer, but only because it's a 1-to-1 ratio. You also needed to recognize that you may, depending upon which of the components you're comparing it to, you may have to have a factor of the molar ratio. So I had molar mass, and I also had molar ratio. Molar mass allowed me to go from the grams to the moles, and then the molar ratio allowed me to go from moles of PbCl2 to moles of Pb2 plus. So writing out, what do I need? Or what do I know? What are my factors that I'm going to need then to employ? All right, I think those are the only two problems. Does that mean everybody else is ready to move on? We had quite a few students who were joining in somewhere in the process of that after our original start. So as you can tell, those of you who came in somewhere along the line, we are reviewing homework questions. We want to make sure everybody is ready as they leave class today so that they can take the test and do well. So far, no one, not a single person has taken the test. So don't feel bad if you came with some confusion or some questions. All right, I see some arrows. I don't see any other questions coming in. So we must be ready to move on. So I'm going to clear my drawings here. We're going to roll forward, and we're going to move on into the next unit that we're going to be studying and learning about. Unit number 12. Unit 12 or module 12 is going to push us into talking about things that are in the gas phase. That's the title of module 12, the gas phase. When we start talking about gases, we're going to have this new property called pressure. So nothing new. You've actually been dealing with pressure all your life, like during the week of a test, right? You feel the pressure of needing to get that done, of wanting to do well, well, this is a different kind of pressure, obviously, but we'll talk about this. Before we do, though, let's take our break because we are at that time. So I'm going to pause, give you a chance to stand up, stretch your legs, walk around, take care of business. We'll come back and then we will jump into module number 12. I'll set a timer so you know how long you've got left. If you want to come back and take a look at the screen, I'll have the timer on the screen for you. We'll take just a little bit more than 4.5 minutes. So you've got enough time to take care of business, and then we will get into module number 12. So we'll see you in a few minutes, everybody. All right, our timer is up, so it's time to go back to work. Did you make it back from your break? If you did, check in on the participant window and let me know. I would appreciate that. And we will go back to sharing our slideshow. There we are. All right, bunch of green checks. Jared, you're still an arrow. I don't know if that means you're back, ready to move on, or still moving on from before, but okay, let's get into this. There we go. Green checks from everybody. Fantastic. Thanks, everybody. All right, so pressure. Pressure is defined as the force per area exerted on an object. And we can actually do force in a variety of different units depending upon the circumstances. Used to be very common and still is a little bit in physics that they would talk about pressure in terms of pascals. They would talk about pressure in terms of pascals because the unit of force that we deal with in physics is newtons. Of course, that word might remind you of cookies, but that's not the kind of Newton we're talking about. Not fig Newtons. We're talking about Newton, who determined the kind of the laws of motion, right? Newton's three laws. So the unit of force was named after him. We call it a Newton. Excuse me. That force pressing in on a certain area. The area is two sides multiplied by each other. So it can be, cubic, or excuse me, it can be square centimeters, square inches. In this case, because we're talking about science, we do things in metric. So it's square meters or meters squared. And those two units then are called a Pascal. Pascal is also named after a particular scientist who was working with these concepts. We typically, though, in chemistry don't deal with things in pascals. We historically measured the pressure in millimeters of mercury. That's the one on the very, very bottom right, 760.0 mmHg. And the reason why we measured them in millimeters of mercury was because, well, that was exactly how we measured it. The way that we would measure pressure is we would have a tube, and that tube would be filled with, nowadays it would be alcohol. Back then it would be mercury. And that tube would be open on the bottom. It would be sitting in a open bath where there is fluid here. And what you would find is that the air would press down on the fluid. That would press up. So if you press down out here, it presses up inside the column. And they literally just had markings. And so in many ways, this barometer would look like a thermometer. A thermometer is basically the same kind of an idea. Once upon a time would have been filled with mercury. Now we use a alcohol solution, but the same effect. When you're put a thermometer in your mouth, it warms the thermometer, it warms the solution inside, and then it goes up a certain amount, and we just read the little readings off of there. Well, that's the way a traditional thermometer was. Nowadays, we use these digital things where they just point them at your forehead or, point them in your ear or whatever it is. But historically, this was the way that we would measure temperature, and it's the way that we would measure pressure. And so millimeters of mercury was our kind of our common unit. If you were to look up the air pressure now on your phone, like on a weather app, a lot of weather apps will tell you what the air pressure is because, well, it has a large role. Air pressure plays a large role in the weather that you're going to get. My app shows my pressure. Let me see if I can find it on this particular app. I got a new phone, so I have a new app, and it's a little different than what my old one had or how it showed me. I'll see if I can find where the pressure is on here. I got temperature, I got rain. This one doesn't actually look like it gives me the pressure. But if you were looking it up, chances are you would actually see the pressure in inches rather than in millimeters, because again, this is America, right? We don't do the metric system here. We tend to push against. Let's go to weather.com. My pressure right now is 29.83 inches. Yeah, Addison's is 30.16. She's a little higher pressure. Of course, probably nicer weather as well. High pressure tends to produce nicer weather. Low pressure tends to produce less nice weather. All right, so anyways, millimeters of mercury was a common way of measuring pressure and expressing pressure. And we still, in some ways, use that in our weather. We talk about it in inches instead of millimeters, but it's the same concept. In science, we more recently have stopped calling it millimeters of mercury because we no longer measure it like this. We no longer are using mercury. And so we've gone to start calling it torr. A torr and a millimeter of mercury are exactly the same. That's why 760 on both of them is equal to 1 ATM. Now, we haven't talked about ATM yet, but you can see that these two things are going to be equal to each other. 1 torr is going to equal 1 millimeter of mercury. Torr and a millimeter of mercury are exactly the same. The only difference is we decided, since we aren't actually using mercury, we should call it something else. More commonly now, we use atmospheres as our unit of pressure. And so you'll see we've put conversion factors on here, all three of them, in terms of atmospheres. And really, atmospheres is something that we came up with based on the standard kind of general pressure found at sea level. And we took that and made that sort of our new standard. And what we find is that when you go up, that the pressure gets less and less. So if you're in Denver at the Mile High City or a mile above sea level, that you have less air pressure than you do at the bottom, if you do at sea level. So the more common unit that we use nowadays is atmospheres, abbreviated ATM. Really, the idea of air pressure is exactly the same, though. There are molecules in the air that are pressing in on you, and you can feel them press in on you. Now, you've felt air pressure on you every day of your life, and so you don't think about it. Your body ignores the feeling of air pressure most of the time. The exception to that is when there is a change in that air pressure over a short period of time. For instance, you maybe have experienced an airplane when you take off or when you land where your ears hurt. Maybe your mom or dad give you a piece of gum to chew or something like that. That motion, you don't even have to have gum in your mouth. You just have to have that motion. That motion alleviates the difference in pressure. The difference in pressure you feel in your ear because your eardrum has air on both sides, and the pressure between them, when the pressure changes in the airplane, in the atmosphere, the pressure inside your ear doesn't change as quickly as the air pressure outside of your ear. And that's why you can feel that. Or you can feel the same thing on a steep hill. If you do a mountain pass or even just a steep hill in the town where you live, you might be able to feel that difference in the pressure on your ear. And really, it's the result because on one side of your ear, if you just think of your eardrum, you've got a certain amount of air molecules and they're pushing against this. And on the outside, they're pushing against this. And what happens as you go down the hill or you go down in an airplane is you get more pressure on the one side. And that difference is what kind of causes that earache, kind of causes that sensation. You're feeling air molecules that are literally pressing in on your ear. Okay, let me move beyond pressure. Once we start to realize that gases exert pressure, we start to study and realize there's a relationship between the volume of the gas and the pressure of the gas. There was a scientist named Boyle who was studying this relationship between pressure and volume, and he discovered that pressure and volume are inversely related. So you have a certain amount of gas molecules. The volume of the gas, one of the things that defines a gas, by the way, we should maybe pause for a moment to acknowledge how gases are different from solids or from liquids, like we've just been studying solutions, right? A solid has a defined volume and a defined shape. A liquid has a defined volume, but an undefined shape. What do I mean by undefined? Well, that means that the shape of the liquid can changes to its container. Well, when we move on then to talk about gas, a gas has an undefined volume and an undefined shape. So a gas can actually change its shape to its container like a liquid does, but a gas will also change its volume to the volume of your container. So as an example, if I have myself a container, well, that's a terrible shaped container. We got to get rid of that bottom there. Let's try that again. There we go. That's a little better. We can create a situation where the volume of the container can change by putting a piston, which can go up or down. When that piston goes down, the amount of space available for a gas changes. Well, what's going to happen if I have a gas down here? Let's assume that this gas has only 5 molecules. 1, 2, 3, 4, 5. Now, one of the things about gases, gas molecules are constantly moving, that they move rather quickly. When those gases are moving around, occasionally they're going to bump against the surface. Whoops, I don't want to draw their arrow that way. Let's make it a small line here. So occasionally it's going to bump against the surface. That's what we know of as pressure. So if I have 5 molecules in this volume of space, they're going to bump against the wall every so often. But what happens when I raise my piston and I increase the amount of space, that is the volume that the gas has access to? Well, now what you're going to find is that those molecules still moving around the container are going to bump into the container a lot less often. So the volume of the gas got bigger. The pressure of the gas got smaller. As I increased the amount of space, we call that volume, the gas would hit the sides of the container less often. You could think about this a little bit like cars on a road. Now, it's kind of a bad example, bad analogy, but it does work. Think about it. When you're in a traffic jam, when there's lots of cars on the road, the chances for an accident, for you to bump into another car, is significantly increased. Driving in traffic and heavy traffic can be very stressful. It can be very frustrating for a variety of reasons, sometimes because we just don't get where we want to go as fast as we want to. But part of it is because you're trying to pay attention. People are changing lanes, people are slamming on their brakes, people are speeding up and taking off. You get all this stuff going on, and you're trying not to hit anybody. But the more cars there are on the road, the harder it becomes to do that. Now, that's a little bit the same way here. Now, if you were to take all that traffic jam and you were to say, well, what if we triple the number of lanes available? So instead of all this traffic on 2 lanes, what if we widen the freeway out and we have 4 lanes, 5 lanes, 6 lanes? Well, now all of a sudden, your cars can be spread out. You find driving isn't stressful anymore. It's kind of fun. You're on your way. And so as we see the cars less likely to bump into each other when they're spread out, the same thing is true about the gas molecules. As the volume increases, the pressure will decrease. Almost wrote that in the wrong direction. That's what we mean by inversely related. So if we were to multiply the pressure times the volume, that answer would be constant, always going to be constant. If you increase the volume, you've got to decrease the pressure in order to still get that constant. If you decrease the pressure, you've got to increase, or excuse me, if you decrease the volume, you've got to increase the pressure in order for that relationship to be constant. Okay, let me move on. That's Boyle's law, pressure and volume. He wasn't the only scientist who was studying gases. Charles is another scientist who was studying gases. Charles was studying the relationship between temperature and volume. So Boyle was studying pressure and volume. Charles was studying temperature and volume. And what he found was that the relationship between temperature and volume was direct. So what does that mean? Well, practically speaking, it means that if you increase the temperature, the volume of the gas will also increase. So again, if we were to take our container and we created it so that there was a way for us to be able to modify that come on now, modify the volume. Now inside we've got our particles of gas, 1, 2, 3, 4, 5. What would happen if you heat up the gas, put a Bunsen burner underneath, that's supposed to be a flame? What happens? Well, what we find is that as we add heat, that the gases here are going to, well, if we didn't change anything, we'd have a different scenario. But since we're studying temperature and volume, that means we're going to allow this piston to move freely. Whoops. And so what would happen is that these gases are going to be more energetic. They're absorbing the heat energy from the Bunsen burner, and that gives them the ability to push this piston up, which would effectively then increase their volume. So as the temperature increases, the volume of the gas increases. Now, as soon as we start talking about temperature and gases, we need to then introduce the idea of the absolute temperature scale. The absolute temperature scale is also called the Kelvin scale. Kelvin was a scientist that we named this after, and it was pretty smart to think about. Right now, when we use Celsius, you know that water freezes at 0 degrees Celsius, and you know that water boils at 100 degrees Celsius. And that's actually how the Celsius scale was determined. They said, well, let's set 0 at where water freezes. Let's set 100 at where water boils. And then we'll divide that into 100 little spaces. And then we'll be able to make that for as hot as we want and as cold as we want. And so, there are times where we live, we can get down into negative temperatures. Now, I lived in the Midwest, and we got to negative temperatures in Fahrenheit. But in the Celsius, it happens all the time. It's not a big deal for us to be -5 degrees Celsius. That's pretty common. The problem with that scale is that you can have negative numbers. And so when you're comparing temperatures, as you would in the Charles law, if you said, well, what if I start out with -5 and my new temperature is +5? That does not mathematically work out the way that you want it to in your answer. The only way this ratio relationship is going to work is if the values that we're using for T, for temperature, are not allowed to go negative. Now, there's another reason why we don't want to allow, or why there's another reason why we want to use the Kelvin scale instead of the Celsius scale. Not only does it make the ratios better, but imagine if you were at freezing and your temperature was 0 degrees. Well, your math would be undefined. You'd be impossible to answer this problem because you cannot have 0 in the denominator of a fraction. It becomes undefined in your calculator. And so Kelvin and other scientists came up with this way where they were able to have a scale for temperature, where the temperature at 0 is at the point where it is the absolute coldest possible. It's called absolute temperature scale because it's like absolute values. There's never a negative number. As a matter of fact, you really can't even get to 0. 0 is a theoretical idea. We can't get to 0 Kelvin. We've been able to get very, very close, but we're not able to get to 0 degrees Kelvin. There's a couple of reasons for why that might be. I won't bore you with the details today because we'll run out of time, but maybe we can talk about it next class. What's important for you is for you to drill into your brain that whenever you're dealing with gases, you must put your temperature into the Kelvin scale. You must convert it to Kelvin. Now, thankfully, that's pretty easy to do. You can see the equation on the board here says, take your temperature in Celsius and you add 273.15, and that will give you your Kelvin. So let me give you a little quick test here, all right? If the room temperature I'm in right now is 21.2 degrees Celsius, what would that be in Kelvin? Did I say 21.2? All right, so Derek's got an answer. Addison's got an answer. Are the rest of you tracking with me? This is super important. While this is not the most important scientific concept in the chapter, it is the source of the largest source of mistakes and wrong answers that students get. That they forget to convert the temperature and they try to work their problems with a temperature in Celsius. That will always get you the wrong answer. Or they make an error in converting their temperature. So you want to make sure you know how to do this. Do you see? It's not that hard, right? Now, there is a problem with everyone's answer so far. Somebody tell me what the problem is with their answer. Significant figures. That's right, Derek. How many significant figures are in the question or in the original temperature? But the number of significant figures isn't what you care about, because this is an addition problem. This is an addition problem, so you don't care about the number of significant figures. Whenever we do addition, we care about the place value of the significant figures. So what we would say is my original temperature is significant to the 10th place. That is 0.1, right? And so my answer must also be significant to the 10th place. Thanks, Whitley. So since 273.15 plus 21.2 equals 294. Yeah, 0.35. 294.35. But I only want my answer to be to the 10th place. I'm going to look at that 5 and ask, do I round up or round down? And of course, I'm going to round up. And so my answer becomes 294.4 Kelvin. Got it? 294.4 Kelvin. So don't forget the rules for significant figures when you're converting temperatures into Kelvin. Okay, so we looked at Charles' law. We looked at Boyle's law. The reality is both of those scientists were looking at gases and wanting to study specific properties and their relationships. And so they were artificially manipulating the circumstances. So Boyle, remember, was looking at the relationship between pressure and volume. And what he was doing is he was saying, what if the temperature could never change? How would a change in pressure affect the volume of the gas? And Charles' law was doing a very similar thing. He was looking at the relationship between temperature and volume. And so he said, what if the pressure never changed? But in reality, gases have the ability to change their pressure, their temperature, and their volume. And so looking at those individual laws is not all that helpful. So it doesn't take very long before, when we're learning about gases, we learn these individual laws, and then we realize that actually the laws can be combined to form a single law, a single mathematical expression that will relate all the variables, pressure, volume, and temperature. Now, what happens? If I change the temperature of the gas, the reality is it can affect the pressure and the volume. But when it does that, it's still going to be this constant. And so we can set up our problems and say, well, if I have a gas and I know how much gas I have to start with, and I can measure the pressure to begin with, and I can measure the temperature to begin with, I can then determine what will the new temperature or pressure or volume be based on other changes. For instance, if I have a gas and I know that that gas is going to undergo a temperature change, I could say, okay, well, if the temperature changes this much, since the container hasn't changed, most of the time the container size stays the same, I can calculate and say, what will the change in the pressure be? Now, that would be important, because if I have a gas that's undergoing a temperature change, and I'm not aware of the fact that it's going to undergo a pressure change, I might find that the container holding the gas isn't built strong enough, that it might explode. That would be very, very bad. You don't want a container to have such high pressure that the container is able to explode, to not hold the gas. Because if that gas volume can't change, but the temperature does, it's going to have a change in pressure. And so we do this with gases in order to be able to determine what the properties will be if the conditions change. So we'll be using the combined gas law quite often. And part of the way that we'll use the combined gas law is to get a gas so that it will be in a range of properties where we can refer to it as an ideal gas. What is an ideal gas? Well, an ideal gas is one in which the size of the molecules, the gas molecules, are very, very, very small in comparison to the volume. Now, I was using examples earlier where I was saying, like, well, what if I have 5 molecules of gas? Well, that's not very many molecules of gas. The reality is, usually when we're dealing with gases, we're dealing with, just like atoms, we're dealing with hundreds of millions, hundreds of thousands of these molecules in a particular situation. And so a lot of times there's a lot of those molecules, but we have to remember that those molecules are super, super, super small. So the actual atomic size is very, very little. As long as the size of the molecules is small in comparison to the overall volume of the gas, then the gas will behave what we call ideally. That will behave ideally. So not only does the size of the molecules need to be small compared to the volume, but the molecules need to be far apart. They need to have no attraction between them. And so we'll sometimes describe this way, okay? And I've maybe done this before for you in class. A solid is when you have molecules and they're kind of stuck together. A liquid is when you have molecules and they're stuck together, but they have the ability to flow past one another. That's why you can pour a liquid out. A gas is one in which you have molecules, and the molecules are constantly moving, but they almost never see one another. They're very far apart from each other. On occasion, though, they will have a random collision where they'll bump into each other. And this is the third part of an ideal gas. When the molecules bump into each other, it's an elastic collision, which means there's no energy lost. Now, if you and I bump into each other, there's going to be some kinetic heat energy created between us through friction. Anytime two surfaces come into contact, there's friction. But what we're saying is that for gases, that's not true. That these gas molecules will bump into each other, and although there's what we would think of as friction between them, we would normally expect that, assume that, there isn't. It's an elastic collision. They will bounce off each other, a lot like you would see a pool cue ball hit another pool ball on the table, and they'll just bounce off each other. One rolls forward, the other one rolls backwards, just the way gases would be. So, okay, for a gas to be ideal, these three things must be true, and they usually are true. We like gases to behave ideally. We like gases to behave ideally, and so we will often place a gas into what we call standard temperature and pressure. We abbreviate this STP, standard temperature and pressure. Standard temperature is 273 degrees Kelvin, or 0 degrees Celsius. Standard pressure is 1 atmosphere. And we like to get a gas into these conditions because then it will behave ideally. When a gas is at STP, it will behave ideally. And really, that allows us then to employ something called the ideal gas law. Now, before we get to that, and we are running out of time here, so real quickly, I want to talk briefly about Dalton's law of partial pressures. And this law makes absolute sense. I just want you to think about it for a second, okay? So if I have a volume container and I put inside that container 5 molecules of gas, those gases are moving around with a certain amount of energy. They're going to push on the sides. That pressure, every time it pushes on the sides, that is what it means for there to be pressure, for that gas to have a pressure. Well, what if I put 5 more molecules into that container? How would that affect the gas? How would that affect the pressure? Well, it does exactly what we would expect. Now, those 5 molecules are going to be able to hit the sides of the container. But the first 5 can also hit the container. And so what we find when we combine gases is that the pressure of those gases are just combined together to create the total pressure. So the total pressure in the system, in my red box, so to speak, is the combination of the gases and their individual pressures. All right, it says the pressure does not depend upon the makeup of the gas, but on the quantity of the gas. So if I had gone in and said, well, what if I put in 10 of a third gas? Well, now this pressure is going to be more than the first two because the volume is going to be the same, but more molecules means it's going to hit the sides more often, so more pressure. But the total pressure in the system is still going to be 1 plus 2 plus 3. I mean, it's not literally 1 plus 2 plus 3, but it's whatever the pressure of gas 1 is, plus the pressure of gas 2, plus the pressure of gas 3. And so the law of partial pressure basically just says that the total pressure is equal to the pressure of the parts combined. All right, we didn't get time to talk about the ideal gas law. You'll cover it in your readings, of course. We could talk about it when we come to class next week. Here is your homework for class 24. Of course, you all have a test today. Nobody took the test yet. And so one of the first things you want to do is make sure that you are reviewed and ready to go for the test that goes from modules 8 through 11. When you're done with that, get started on this week's work, which is module 12. Module 12 is all about gases. And as you do always, when you come to a new module, you're going to read it, take notes. You come to a problem, you want to solve it. Once you've solved it, you want to check your answer. If you got it wrong, you want to correct your work. Don't just change your answer, correct your work. As you come to an experiment, if there are any, you want to complete them so that you have that concrete experience. But we're not assigning anything for the labs this week. If you were to go in and look in the Module 12 folder, you will see that there is a lab report for 12.1 next week, but not this week. So the idea is this week you'll do the experiment, next week you'll write the lab report. And so be aware of that. Make sure that you take good notes as you go through and conduct your experiment so that you can produce your lab report next week. Okay, that's it for class 24. Thanks everybody for being here. Blessings to you. Have a good week. Email me if you need some help. I'll keep praying for you as you take your test today and look forward to seeing you next Monday. Bye-bye till then.